What if I told you that every atom in your body, every star in the night sky, even the very fabric of reality as we know it, traces back to a single, transformative moment in cosmic history? A moment so profound it rewrote the rules of existence itself. That moment is called the cosmic dawn, the universe's first sunrise, when darkness gave way to light, and the cosmos as we recognize it began to take shape. Picture this, an endless void, cold and silent, suddenly sparking to life with the birth of the very first stars. These weren't just any stars, they were titans, blazing with such intensity that their light stretched across billions of years, carrying secrets we're only now beginning to understand. This is where our journey begins. In 20 Chronicles of the Cosmic Dawn, we're not just recounting events, we're stepping into a time machine, peeling back layers of cosmic history to witness the universe in its infancy. Imagine standing at the edge of creation, watching as the first galaxies flicker to life, their light so faint it's like trying to hear a whisper across an ocean. Yet, these whispers hold answers to questions that have haunted humanity for centuries. Where did we come from? How did the chaos of the early universe give rise to the order we see today? And what does it all mean for our place in the cosmos? But here's the thing, the cosmic dawn isn't just a story for astronomers, it's a story about us. Every element in your body, from the calcium in your bones to the iron in your blood, was forged in the hearts of those first stars. Their explosions seeded the universe with the building blocks of planets, oceans, and life itself. So when we study this era, we're not just exploring distant galaxies, we're uncovering our own origin story. Over the next 20 chapters, we'll dive into the most groundbreaking discoveries, the unsolved mysteries, and the mind-bending theories that challenge everything we thought we knew. From the faint echoes of ancient light to the cosmic web that binds the universe together, this is a journey that will change how you see the night sky and your place within it. So, are you ready to travel back to the dawn of everything? Let's begin. Long before the first stars flickered to life, the universe was a seething ocean of raw energy, a place so extreme, so alien, that even the simplest atoms couldn't yet exist. This was the aftermath of the Big Bang, a cosmic forge where space itself expanded faster than light, stretching matter into a thin, scorching haze. But as the universe cooled, something extraordinary was left behind, a faint whisper of heat, a ghostly glow we now call the cosmic microwave background. Think of it as the universe's baby picture, a snapshot taken when everything was just 380,000 years old. This ancient light isn't just a relic, it's a treasure map. Hidden within its subtle ripples are the seeds of everything we see today. Picture the cosmic microwave background as the surface of a pond, with tiny waves frozen in time. Those ripples are density variations, slightly thicker patches of gas, where gravity would eventually work its magic, pulling matter together until the first stars ignited. Telescopes like Planck and WMAP have spent decades studying these patterns, and what they've revealed is astonishing. The universe's infancy wasn't smooth or uniform. It had texture, like a canvas primed for creation, but here's the real wonder, those subtle imperfections were destiny. The denser regions became the nurseries for galaxies, while the emptier stretches evolved into the vast voids between them. It's as if the universe was programmed from the start, its fate written in those first flickers of heat. And the most mind-bending part, we're literally bathing in this ancient glow every second. The static on an old television, about 1% of that snow, comes directly from the Big Bang's afterglow, a signal traveling across 13.8 billion years to reach you. Yet the cosmic microwave background isn't just a time capsule, it's a detective. By studying its polarization, scientists have uncovered clues about the universe's very first moments, even before atoms formed. Some theories suggest these patterns might hint at cosmic inflation, a blink of time when the universe expanded exponentially faster than the speed of light. Others believe they could reveal hidden dimensions or the nature of dark matter. Every new observation peels back another layer, bringing us closer to understanding how a scorching, chaotic infancy gave rise to the ordered cosmos we call home. So when we look at that faint microwave glow, we're not just seeing light, we're staring into the foundation of reality itself. The stage was set, the conditions perfect. All that remained was for the darkness to give way, for the first sparks to ignite, and for the cosmic dawn to begin. Imagine a universe so dark and silent that not a single star pierces the endless night. No galaxies spin in the void, no planets orbit unseen suns, just an ocean of neutral hydrogen gas, stretching cold and featureless across the cosmos. This was the universe during its forgotten adolescence, the Dark Ages, a mysterious epoch that lasted for hundreds of millions of years after the Big Bang's afterglow faded. It's a chapter in cosmic history so obscure, scientists call it the universe's missing link, the bridge between the fire of creation and the first sparks of starlight. Why does this era remain so elusive? Without stars, there was no light to illuminate the darkness. Without galaxies, there were no landmarks to map the void. The cosmic microwave background, our last clear snapshot of the infant universe, had already faded into radio waves, leaving astronomers with what seems like a blank page in the story of everything. But hidden within that darkness are clues written in the whispers of hydrogen itself. During this time, the universe wasn't truly empty, it was a cosmic womb, quietly nurturing the seeds of structure. Those subtle ripples we saw in the microwave background, they were growing, ever so slowly, as gravity began to pull matter into the faintest of clusters. Here's where it gets fascinating. The hydrogen gas of the Dark Ages wasn't just sitting idle, it was absorbing light. Any faint radiation trying to travel through it would be snuffed out, like a fog swallowing a lantern's glow. That's why astronomers search for shadows in the cosmic record, looking for places where hydrogen absorbed the faintest radio waves from even earlier times. It's like listening for echoes in a cave, hoping to reconstruct its shape from the silence, but the Dark Ages weren't destined to last. Somewhere in that vast, featureless expanse, gravity finally gained the upper hand. Denser regions of gas began collapsing under their own weight, heating up until, at last, the first protostars ignited. These weren't the stars we know today. They were monsters, hundreds of times more massive than our sun, burning hot and fast before exploding in titanic supernova. Their deaths would flood the universe with the first heavy elements, recycling chaos into the building blocks of planets, oceans, and life. Yet the mystery remains: how exactly did the cosmos transition from this silent era to the light-filled universe we know? The answer might lie in the fingerprints left behind by those first stars. As they ignited, their ultraviolet radiation ripped electrons from hydrogen atoms, reionizing the gas and ending the Dark Ages in a cosmic sunrise. Telescopes like the James Webb are now scouring the deepest reaches of space, hunting for the faintest glimmers of that transformation. Every photon they catch is a message from the edge of time itself, a clue to how darkness first gave way to light. So when we peer into this shadowy epoch, we're not just studying an ancient era, we're uncovering the moment the universe woke up. The Dark Ages weren't a pause in cosmic history, they were the quiet before the storm, the prelude to everything we see today, and somewhere in that stillness, the fate of galaxies and perhaps even life itself, was being written in the dark. The first stars didn't just light up the cosmos, they rewrote the rules of existence. Born from pristine clouds of hydrogen and helium, untouched by the heavier elements that fill our universe today, these celestial titans, known as population 3 stars, were unlike anything we've ever seen. Imagine a star so massive it dwarfs our sun by hundreds of times, burning at temperatures so extreme its life was measured in mere millions of years instead of billions. Their brilliance was fleeting, but their impact eternal. These weren't just stars, they were cosmic alchemists. When their short, violent lives ended in colossal supernova, they didn't fade quietly. They exploded with such force that they forged entirely new elements in their cores, scattering carbon, oxygen, and iron across the void. For the first time, the universe had more than just hydrogen and helium. It had the building blocks of planets, oceans, and life itself. Every mountain, every breath of air, every drop of water in your body owes its existence to those cataclysmic deaths. But here's the catch: we've never directly seen one of these ancient giants. They vanished billions of years ago, their light lost to the depths of time. So how do we know they existed? The answer lies in their fingerprints. Modern telescopes detect traces of their handiwork in the oldest, most distant galaxies, where the chemistry of their explosions still lingers. Even the gas between galaxies holds clues, carrying faint echoes of those first heavy elements. Scientists use supercomputers to simulate their births, revealing just how strange these stars must have been. Without heavier elements to help them cool, the gas clouds that formed them collapsed into monsters, far larger than any star born today. Their deaths were equally extreme. Some may have even imploded into early black holes, seeding the universe with the gravitational anchors around which galaxies would later grow. Yet mysteries remain. Could fragments of these ancient stars still drift through space, hidden in the outskirts of our galaxy? Some theories suggest that a handful of ultra-old, metal-poor stars might be the last survivors of that primordial era, carrying the untainted chemistry of the early cosmos. Others hunt for the ghostly remnants of their supernova, long, cooled bubbles of gas marking where they once blazed. The legacy of population 3 stars isn't just written in the elements they created. It's etched into the structure of reality itself. They transformed the universe from a simple, dark place into a complex tapestry of chemistry and light, a tapestry we're still unraveling today. So when you look up at the night sky, remember, those distant points of light are the children of giants, and somewhere in the darkness between them, the echoes of the very first stars still whisper. The universe didn't just wake from the dark ages, it exploded into light with a violence that reshaped everything. As the first stars and galaxies ignited, their ultraviolet radiation blasted through space like a cosmic wildfire, stripping electrons from the neutral hydrogen gas that had blanketed the cosmos. This was reionization, a revolution so profound it turned the universe transparent, burning away the fog that had hidden the dawn of creation for hundreds of millions of years. Picture it as a cosmic game of dominoes. The first massive stars lived fast and died young, their supernova scattering heavy elements while their radiation carved bubbles of ionized gas around them. Over time, these bubbles grew, merging as new stars and galaxies joined the fray. But here's the twist: reionization wasn't uniform. Some regions of the universe lit up early, while others clung to darkness longer, creating a patchwork of light and shadow. Telescopes like Hubble and James Webb are now mapping these ancient battle lines, spotting distant quasars, supermassive black holes, shining brighter than entire galaxies, whose light bears the scars of passing through the last pockets of neutral hydrogen. Why the unevenness? The answer might lie in the universe's very architecture. Density fluctuations left over from the Big Bang meant some areas had a head start, with more gas collapsing into stars faster. Or perhaps early black holes played a role, their jets shredding surrounding hydrogen like cosmic blowtorches. There's even evidence that dwarf galaxies, too faint to see directly, might have been the unsung heroes of reionization, their collective starlight adding up to a transformative force. Every discovery peels back another layer. When the James Webb Space Telescope detected galaxies brighter and more mature than expected in the early universe, it threw a wrench into existing timelines. Could reionization have started earlier than we thought, or did those first stars burn hotter and faster, attacking the hydrogen fog with unexpected fury? Each observation is a puzzle piece, forcing us to redraw the maps of cosmic history. The stakes couldn't be higher. Reionization didn't just clear the cosmic stage, it set the rules for everything that followed. Without it, light would still struggle to travel freely, and modern galaxies might never have formed. We're essentially seeing the moment the universe became recognizable, the moment it turned the page from chaos to the first chapters of structure. And as telescopes probe deeper, they're not just capturing snapshots of the past. They're revealing how fragile the balance was between light and darkness, and how easily the story could have unfolded differently. At the heart of the cosmic dawn, hidden in the swirling chaos of the first galaxies, cosmic monsters were already taking shape. Supermassive black holes, some weighing billions of times the mass of our sun, emerged with shocking speed, far sooner than modern theories predicted. How could such behemoths exist when the universe was barely out of its infancy? The answer might rewrite everything we know about cosmic evolution. These weren't just any black holes. They were engines of destruction and creation, feasting on gas so voraciously they became quasars, objects so bright they outshone entire galaxies. Their radiation blasted across space, heating surrounding gas and strangling star formation in some regions while triggering it in others. Picture a cosmic sculptor, carving voids and filaments into the universe with jets of energy powerful enough to rearrange matter on staggering scales. So how did they grow so massive so fast? One theory points to the death throes of population. 3 stars, those primordial giants that collapsed directly into black holes without the usual supernova fireworks. Another possibility is even more radical: vast clouds of pristine gas, untouched by heavier elements, collapsing under their own weight in a single, catastrophic plunge. These direct collapse, black holes could have sprung into existence with masses thousands of times greater than the Sun, giving them a head start in the race to become supermassive. Recent discoveries have only deepened the mystery. The James Webb Space Telescope has spotted quasars glowing in the universe's toddler years, their existence defying conventional timelines. Some show evidence of having already merged, their growth turbocharged by collisions in the crowded early cosmos. Others appear to have shut off abruptly, as if starved of fuel by their own violent outbursts. Each observation chips away at our understanding, suggesting black holes didn't just grow alongside galaxies, they may have shaped them from the beginning. The most tantalizing question remains: did these ancient black holes lay the groundwork for the universe we see today? Their gravity could have acted like cosmic anchors, drawing in gas and dark matter to form the first galactic cores. Their eruptions might have carved the vast voids and filaments of the cosmic web, determining where future galaxies would bloom. In a very real sense, the night sky we gaze upon, with its glittering cities of stars, could be the legacy of monsters we're only just beginning to comprehend. Every new quasar discovered pushes the boundaries of what we thought possible, forcing us to rethink how chaos gave way to order. These weren't mere bystanders in cosmic history. They were the architects, the destroyers, and perhaps even the midwives of the universe itself. And as we peer further back in time, their whispers grow louder, challenging us to unravel the secrets of the darkest, most influential entities in existence. The universe didn't just scatter galaxies randomly, it wove them into an intricate tapestry, a cosmic web so vast it defies imagination. Picture this: billions of galaxies strung like pearls along invisible threads, stretching across billions of light years in a delicate, spider-like structure. But this web wasn't spun overnight. Its origins trace back to those faint ripples in the newborn universe, the same density variations imprinted in the cosmic microwave background. Over eons, gravity amplified those subtle wrinkles, pulling matter into filaments of dark matter, an invisible skeleton that would dictate where galaxies could bloom. Dark matter is the unseen architect of this web. Unlike ordinary matter, it doesn't interact with light, but its gravitational pull is irresistible. Supercomputer simulations show how these mysterious particles clumped first, forming a vast network of tendrils. Ordinary matter, the gas that would become stars and galaxies, simply flowed into the valleys carved by dark matter's gravity. The result: a universe where galaxies cluster along filaments like dew on a spider's silk, with vast, empty voids stretching between them. Some of these cosmic highways are so immense they dwarf entire superclusters, weaving a structure that's both breathtaking and humbling. But the cosmic web isn't just a static blueprint, it's a dynamic, evolving entity. Dark energy, the force accelerating the universe's expansion, stretches these filaments over time, pulling them thinner and driving galaxies farther apart. Yet even as the web's strands grow more diffuse, their influence remains. Collisions between clusters of galaxies send shockwaves along these filaments, heating gas to millions of degrees and creating some of the hottest places in the universe. Meanwhile, the web itself acts as a cosmic conveyor belt, funneling fresh gas into galaxies, fueling new generations of stars. The most astonishing part: we can actually map this invisible architecture. Astronomers use the light from distant quasars to trace the web's structure. As their light passes through filaments of hydrogen gas, it leaves absorption lines like fingerprints in the quasar's spectrum. Other techniques rely on gravitational lensing, where the web's mass bends light from even more distant objects, revealing its hidden contours. Each new map peels back another layer, showing how the universe organized itself on the grandest scale imaginable. What does the cosmic web teach us about the universe's fate? Its structure is a battleground between dark matter's gravity and dark energy's relentless push. If dark energy prevails, the web may one day stretch so thin that galaxies become isolated islands in an ever-expanding void. But for now, it stands as a testament to the universe's hidden order, reminder that even in the chaos of the cosmic dawn, the seeds of structure were already sown. Every galaxy, every star, and every atom in your body exists because gravity traced these threads across the darkness, weaving the story of everything into existence. Without dark matter, the night sky would be empty: no galaxies, no stars, just endless blackness. This invisible substance, outweighing ordinary matter 5-1, is the unsung hero of the cosmic dawn, the silent force sculpting the universe into the structured cosmos we know today. Think of it as cosmic scaffolding, a hidden framework that guided the first wisps of gas into the building blocks of galaxies, while the rest of the universe was still shrouded in darkness. What makes dark matter so baffling It doesn't absorb, reflect, or emit light, meaning even our most powerful telescopes can't see it directly, yet its gravitational fingerprints are everywhere. When astronomers measure the rotation speeds of galaxies, they find stars whirling so fast that without some unseen mass holding them together, they'd fling into the void. The same goes for galaxy clusters, where visible matter alone can't explain the way gravity bends light around them like a lens. These observations all point to one conclusion: dark matter isn't just real, it's the universe's dominant architect. So what is it? Leading theories propose particles unlike anything in the standard model. Weakly interacting massive particles, or WIMP, are heavyweight candidates, ghostly entities that barely interact with ordinary matter except through gravity. Then there are actions, ultralight particles born from quantum field theory, so ethereal they could pass through a planet like moonlight through glass. Some experiments hunt for these phantom particles in tunnels deep underground, shielded from cosmic interference, while others scan space for gamma rays that might betray dark matter collisions. Yet the greatest clues come from the cosmic dawn itself. Simulations show that without dark matter's gravitational pull, ordinary matter would have dispersed too thinly, never clumping densely enough to ignite the first stars. It acted like a cosmic sieve, gathering hydrogen gas into the denser pockets where gravity could take over. The twist: dark matter's behavior in those critical early moments doesn't always align with predictions. Some ancient galaxies appear too compact, their dark matter, halos, strangely concentrated, hinting that our models might be missing a piece of the puzzle. The stakes couldn't be higher. If dark matter particles interact with each other in unexpected ways, or if they're part of a richer, undiscovered physics, it could reshape our understanding of cosmic evolution. Telescopes like Euclid and Vera Rubin Observatory are mapping its distribution with unprecedented precision, tracing how its web-like structure evolved over billions of years. Meanwhile, theorists explore radical ideas. Could dark matter have formed black holes in the universe's first second? Might it decay into exotic energy? Every unanswered question is a thread in the tapestry of cosmic history. Dark matter didn't just enable the universe's first light, it dictated where and when that light could shine. And as we peel back its mysteries, we're not just uncovering the past, we're reading the hidden blueprint of reality itself. The first galaxies didn't emerge gracefully. They erupted from the chaos of the cosmic dawn like sparks from a forge, tiny and frenzied, nothing like the orderly spirals we recognize today. Imagine a cosmic construction site, where a single galaxy might span just a fraction of the Milky Way's size, yet blaze with the energy of 1,000 suns. These primordial islands of stars were far denser, their gas clouds colliding and collapsing at breakneck speed, birthing new stars at rates that would put modern galaxies to shame. Recent observations from the James Webb Space Telescope have upended our assumptions about these ancient systems. Some galaxies from this era are shockingly massive, appearing fully formed when the universe was barely 5% of its current age. Others glow with unexpected brightness, their starlight amplified by dense clusters of stars packed into regions smaller than our solar system. These discoveries aren't just anomalies, they're forcing astronomers to rethink how galaxies assemble in the first place. The prevailing theory suggested galaxies grew slowly, like trees, accumulating mass over billions of years through gentle mergers and steady gas inflows. But the early universe had no patience for slow and steady. Galactic collisions were frequent and violent, with smaller protogalaxies smashing together in bursts of star formation, so intense they could outshine entire modern galaxies. Supermassive black holes, already lurking at their cores, may have acted like cosmic blowtorches, heating surrounding gas and triggering even more star birth in a feedback loop of creation and destruction. Here's where it gets even stranger. Some of these galaxies appear too old for their age, packed with mature stars that shouldn't have had time to form. One explanation: the first stars might have ignited earlier than we thought, in pockets of the universe where matter was denser, jump-starting galaxy growth before the cosmic clock officially began ticking. Alternatively, dark matter could have clumped more efficiently in certain regions, accelerating the birth of galaxies in ways our models didn't predict. The implications ripple across cosmology. If galaxies formed faster and more efficiently than theorized, it could mean the universe's early structures were fundamentally different, perhaps shaped by exotic physics we haven't yet accounted for. Every new web image peering back to this era is like finding a page torn from a cosmic instruction manual, one where the rules seem both familiar and wildly alien. Yet amidst the chaos, patterns emerge. These galaxies, for all their strangeness, still follow the universe's deepest rhythms: gravity pulling gas into stars, stars enriching space with heavy elements, and black holes shaping their surroundings. They're not just ancient relics, they're blueprints, showing us how the tiniest fluctuations in the primordial universe snowballed into the vast structures we see today. And as we uncover more of their secrets, we're not just studying the past, we're deciphering the origins of order itself. Among the first monsters to emerge from the cosmic darkness, quasars burned with a brilliance that defied logic, their light so intense it could outshine entire galaxies. But these weren't just cosmic lighthouses, they were the engines of transformation, reshaping the universe around them. At their cores lurked supermassive black holes, some weighing billions of times the mass of our sun, feasting on gas so violently that the friction of infalling matter heated it to millions of degrees, turning their surroundings into swirling maelstroms of radiation. A single quasar could unleash enough energy in 1 second to power human civilization for billions of years, yet their true power lay not just in their light, but in their influence. Quasars acted like cosmic blowtorches, their ultraviolet radiation stripping electrons from hydrogen atoms across vast distances, carving bubbles of ionized gas that accelerated the end of the universe's dark ages. In some regions, their fury was so extreme it suppressed star formation entirely, heating gas to temperatures too high for gravity to pull it into new stars. Imagine neighborhoods where the very fabric of creation was sterilized by these blazing behemoths, leaving behind voids that would take eons to refill with cool, star-forming material. But quasars were also paradoxically creative. Their relativistic jets, narrow beams of plasma racing near light speed, could span millions of light years, ramming into surrounding gas clouds and triggering shockwaves that compressed matter, sparking bursts of star birth in their wake. Some galaxies owe their very shape to these eruptions, their spiral arms sculpted by ancient quasar winds. Even more astonishing, quasars may have acted as cosmic couriers, their radiation pressure propelling heavy elements like carbon and oxygen across intergalactic space, seeding future generations of stars and planets with the ingredients for life. Why did some corners of the early universe teem with quasars while others lay quiet? The answer might lie in the chaotic mergers of young galaxies. When two gas-rich galaxies collided, their central black holes could merge, while fresh torrents of gas fed the resulting monster, igniting a quasar phase. Denser regions of the cosmic web, where galaxies clustered tightly, became quasar hotspots, while isolated patches remained dark. Yet puzzles remain. Some quasars flicker unpredictably, their light curves suggesting they might be cloaked in thick shrouds of dust, or that their feeding black holes burp intermittently as gas swirls inward in uneven waves. Every flicker in a quasar's light carries a message. Variations in their brightness reveal the turbulent environments around their black holes, while absorption lines in their spectra map the distant gas clouds their light has pierced. Some quasars even serve as cosmic yardsticks, their redshifts acting as mile markers in the expanding universe. And as telescopes peer deeper, they're uncovering quasars from shockingly early times, existing when the cosmos was barely 700 million years old. Their very existence challenges theories about how black holes could grow so massive, so fast. The epoch of quasars wasn't just a chapter in cosmic history, it was a revolution. These luminous giants didn't merely light up the universe, they forged its future, their explosive lives and deaths setting the stage for the quieter, more stable cosmos we inhabit today. And as we decode their flickering signals, we're not just studying ancient relics, we're witnessing the moment the universe learned to wield its own darkness as a tool for creation. We think we know the universe, the stars, the galaxies, the planets, until science pulls back the curtain and reveals another enigma. Take ordinary matter, the atoms that make up everything from your morning coffee to distant supernova. It should be easy to account for, right? Yet here's the cosmic twist. Half of it is missing, not hidden in black holes or tucked inside dark matter, but simply gone. Or so we thought. The truth is stranger. These lost baryons are all around us, floating invisibly in the vast spaces between galaxies, woven into a faint, hot web of gas so diffuse it's like trying to spot a single candle flame from 1,000 miles away. This warm, hot intergalactic medium, or WIM, is the universe's best-kept secret. Theorists predicted its existence decades ago, a ghostly reservoir of protons and electrons, heated to millions of degrees but spread so thin it emits only the faintest X-ray whispers. For years, our telescopes weren't sensitive enough to catch those whispers. The missing baryons were right under our noses, blending into the cosmic background like ink dissolved in an ocean. But now, cutting-edge instruments like the XMM Newton and Chandra X-ray Observatory are finally piecing together the clues. They've spotted subtle distortions in the light of distant quasars, tiny dips in brightness where WIM ionized gas has absorbed specific wavelengths. It's as if we've discovered a hidden river system flowing between the islands of galaxies. How did this matter go unnoticed for so long? Blame the universe's own trickery. When gas heats to extreme temperatures, it doesn't glow like a star. It becomes nearly transparent, emitting X-rays too faint for older telescopes to distinguish from background noise. Worse, this gas isn't evenly distributed. It clumps along the filaments of the cosmic web, tracing the same dark matter scaffolding that shapes the universe's large-scale structure. To map it, astronomers must stitch together thousands of observations, like reconstructing a fresco from scattered flakes of paint. The hunt gets even trickier when you consider the WIM dynamic nature. Gravity constantly tugs at these baryons, pulling some into galaxies while supernova and black holes blast others back into intergalactic space. It's a cosmic recycling program on the grandest scale, with matter evaporating and condensing like breath on a cold window. Some of the gas may have been ejected during the universe's most violent teenage years, when young galaxies spewed out material in chaotic outbursts. Other portions might be primordial, lingering undisturbed since the Big Bang. Why does finding these baryons matter? Because without them, our cosmic ledger doesn't balance. The laws of physics tell us exactly how much ordinary matter should exist based on the early universe's conditions, But until we account for every atom, we're missing a critical piece of the puzzle. The WIM isn't just hiding matter, it could hold clues to how galaxies form and evolve, why certain regions of space are star-rich while others are deserts, even how heavy elements spread across the cosmos. New missions like ESA's Athena telescope promise to bring this shadowy realm into focus, probing deeper into the X-ray spectrum with unprecedented precision. Every flicker of detected gas adds another stroke to the map, revealing a universe far richer and more intricate than we ever imagined. The missing baryons aren't lost, they've been waiting, quietly shaping the cosmos from the shadows. And as we trace their faint signatures, we're not just solving a mystery, we're learning to read the universe's hidden ledger, one atom at a time. Long before the first stars ignited, before galaxies took shape, even before the cosmic fog of the Dark Ages settled in, the universe was quietly conducting its first chemistry experiment. In the cooling aftermath of the Big Bang, as temperatures plummeted from billions of degrees to mere thousands, particles that had raced freely through the searing plasma finally slowed enough to bond. Here, in this primordial crucible, the first molecules were born. Hydrogen-helium hydride, or He-H+, a simple union of a hydrogen atom and a helium ion, became the universe's inaugural chemical handshake. It wasn't glamorous, just two humble elements clinging together in the cooling void, but this molecule, and others like it, laid the groundwork for everything that followed. These first molecules weren't just relics, they were cosmic refrigerators. As the early universe expanded, it needed a way to shed heat, to transition from a roiling plasma to a cooler, more structured state. Molecules like He-H+ acted like radiators, absorbing energy through collisions and re-emitting it as infrared radiation, allowing gas clouds to lose heat and contract. Without this cooling mechanism, gravity wouldn't have stood a chance against the pressure of hot gas, and the first stars might never have formed. Think of it like a campfire cooling embers so new logs can catch, a delicate balance between energy loss and collapse. For decades, He-H+ existed only in theory, its fingerprints erased by time. Then, in 2019, astronomers spotted its faint signal in a planetary nebula thousands of light-years away. While not primordial, this molecule formed later in the nebula's life. Its detection proved that He-H+ could survive in space, a breakthrough that opened the door to hunting its ancient counterparts. Telescopes like SOFIA, the Airborne Observatory, and ALMA, the Radio Telescope Array, are now tuned to listen for these whispers from the cosmic dawn, scanning distant gas clouds for the spectral signatures of molecules forged in the universe's infancy. But He-H+ was just the beginning. As the cosmos cooled further, hydrogen molecules, or H2, began to dominate. A far more efficient coolant, these molecules would become the workhorses of star formation, enabling gas to condense into the dense cores where nuclear fusion could ignite. Some theories suggest that without these early molecules, the universe might have remained a featureless haze, never birthing the blazing stars and galaxies we see today. The hunt for these primordial molecules is more than a scientific curiosity. It's a direct line to the universe's chemical origins. Every detection peels back another layer of cosmic history, revealing how chaos gave way to order and how simple bonds between atoms set the stage for the dazzling complexity of planets, life, and us. So when we study these ancient molecules, we're not just analyzing chemistry, we're uncovering the recipe for existence itself. What if the universe began not with a bang, but with a burst, a split-second expansion, so violent it stretched space itself faster than light could chase it? This is cosmic inflation, the theory that in the first trillionth of a trillionth of a trillionth of a second, the cosmos ballooned from smaller than an atom to the size of a grapefruit. But inflation didn't just make space bigger, it encoded the blueprint for everything to come, from the first stars to the web of galaxies we see today. And the evidence might be hiding in the faintest whispers of the cosmic dawn. Imagine the infant universe as a ball of dough with tiny, random lumps. Inflation stretched those lumps exponentially, magnifying microscopic quantum fluctuations into cosmic-scale wrinkles, regions slightly denser or hotter than their surroundings. Those imperfections became the seeds for galaxies, their gravity pulling matter into the structures we recognize now. But inflation didn't just leave its mark in matter. It should have generated something far more elusive: primordial gravitational waves, ripples in spacetime itself that would have propagated outward like echoes from the Big Bang's first heartbeat. Detecting these waves would be like finding the universe's birth certificate. Experiments like BICEP and the Planck satellite scan the cosmic microwave background for a telltale twist in the polarization of ancient light, a swirling pattern called B modes that could only be imprinted by gravitational waves. So far, the results are tantalizing but inconclusive, like hearing a faint hum just below the threshold of certainty. Future missions, like NASA's proposed Light-Bird satellite or next-generation ground-based telescopes, aim to listen more closely, filtering out cosmic interference to isolate inflation's signature. Why does this matter? Because inflation doesn't just explain the universe's size or smoothness. It answers deeper questions. Without it, the cosmos would lack the delicate balance needed for galaxies to form. Regions too dense would collapse into black holes. Regions too sparse would remain barren. Inflation fine-tuned the universe's initial conditions with razor precision, setting the stage for the cosmic dawn's light to eventually emerge. Some theories even suggest multiple episodes of inflation, with our universe just one bubble in a frothing multiverse. Yet mysteries linger. If gravitational waves are confirmed, their strength could reveal inflation's energy scale, exposing physics far beyond the reach of particle colliders. Alternatively, their absence might force us to rethink inflation altogether, pivoting to rival theories like bouncing cosmologies or emergent spacetime. Either way, the hunt for these ripples isn't just about validating a theory, it's about decoding the universe's first instruction, the command that set the cosmos in motion. And as we peer deeper into the cosmic dawn's afterglow, we're not just studying the past, we're reading the first line of reality's autobiography. The first stars didn't just fade away, they went out in explosions of cosmic violence so spectacular they shaped the destiny of the universe. Most met their end in supernova, detonating with such force that their cores fused lighter elements into heavier ones, scattering carbon, oxygen, and iron across space like celestial breadcrumbs. But not all of these primordial giants died the same way. Some may have bypassed the fireworks entirely, collapsing silently into black holes so dense not even light could escape. Others might have birthed something even stranger: dark stars, hypothetical monsters powered not by nuclear fusion, but by the annihilation of dark matter itself. Take supernova first. When the earliest stars, those behemoths hundreds of times more massive than our sun, exhausted their fuel, their cores imploded under gravity's crushing weight. The shockwaves from this collapse rebounded outward, blasting the star's outer layers into space at nearly a tenth the speed of light. These explosions were far more energetic than anything seen today, seeding the cosmos with the first heavy elements. Without them, planets, oceans, and life as we know it wouldn't exist. But here's the twist: some of these supernova might have been pair instability events so powerful they left no remnant behind, just a void where a star once blazed. Then there were the silent disappearances, stars on the more massive end of the spectrum, perhaps above 260 solar masses, may have avoided supernova entirely. Their gravity was so overwhelming that when their cores collapsed, no explosion could halt the process. Instead, they simply vanished, leaving behind black holes that siphoned up surrounding gas like cosmic vacuums. These primordial black holes could have been the seeds for the supermassive monsters we now find at the centers of galaxies, growing rapidly by feasting on the dense gas of the early universe. But the strangest fate of all might belong to the dark stars. Theorized to exist in regions dense with dark matter, these stellar anomalies could have drawn energy from dark matter particles, annihilating each other in their cores. Unlike ordinary stars, they wouldn't have relied on fusion, burning cool yet colossal, some possibly reaching sizes larger than our entire solar system. Though they've never been observed directly, their existence could explain anomalies in the early universe's light patterns, or even account for some of the mysterious dark matter we still can't detect. The remnants of these stellar pioneers are still with us. Ultra-metal, poor stars hiding in the Milky Way's halo might be second-generation survivors, forged from the ashes of a single population, 3 supernova. Their chemical fingerprints bear traces of elements heavier than helium act as time capsules, preserving the composition of the universe's first stellar deaths. Even the gas between stars holds clues, with some regions bearing the isotopic signatures of those early explosions. The deaths of the first stars weren't just endings, they were transformations. Every atom heavier than hydrogen and helium, every black hole anchoring a galaxy, even the potential echoes of dark stars, all trace back to these cataclysms. Their legacy isn't just written in the elements they created, but in the very structure of reality. And as we sift through their ashes, we're not just studying the past, we're holding pieces of the universe's first obituary, written in stardust. Deep in the heart of modern cosmology lies a mystery so perplexing it threatens to unravel our understanding of the universe itself. It's called the Hubble Tension, a stubborn disagreement between two seemingly foolproof methods of measuring how fast the cosmos is expanding. On one side, we have the cosmic microwave background, that ancient afterglow from the Big Bang, suggesting a precise expansion rate. On the other, observations of nearby galaxies and supernova insist the universe is ballooning significantly faster. These aren't small margins of error. We're talking about a discrepancy that would make the universe billions of years younger in one calculation than the other. Something fundamental is missing from our equations, and the clues might be hidden in the relics of the cosmic dawn. This isn't just academic quibbling. The expansion rate tells us how old the universe is, what it's made of, and how it will end. If our measurements can't agree, it means we might be misunderstanding the very fabric of reality. Some theorists suggest exotic solutions, perhaps dark energy isn't constant but evolves over time, growing stronger as the universe ages. Others speculate about undiscovered particles that briefly flooded the early cosmos, altering the expansion rate in ways we haven't accounted for. Then there's the radical possibility that gravity itself behaves differently on cosmic scales, bending the rules we thought were set in stone. Here's where the cosmic dawn becomes crucial. The formation of the first stars and galaxies didn't just light up the universe. It left subtle imprints in the distribution of matter we can still detect today. By mapping hydrogen gas from this era, using radio telescopes like the Hydrogen Epoch of Reionization Array, Astronomers are hunting for anomalies in how structures clustered in the early universe. If the density of primordial gas varies in unexpected ways, it could point to unknown forces tweaking the expansion rate during those critical first billion years. The most tantalizing leads come from the cosmic microwave background's finer details. Tiny deviations in its polarization patterns might reveal whether dark energy interacted differently with matter in the past, or if additional relativistic particles, remnants from the universe's fiery birth, gave expansion an extra nudge. Projects like the Simons Observatory and next-generation space telescopes are racing to collect this data, knowing it could rewrite cosmology textbooks. What's at stake goes beyond bragging rights for which measurement is correct. If the tension persists, it may signal that our standard model of cosmology, the beautifully precise framework that explains everything from galaxy formation to the abundance of light elements, is incomplete. We might be standing at the threshold of a revolution where the answers don't just resolve the Hubble tension, but unveil entirely new physics governing the cosmos. Every observation of the cosmic dawn's fading echoes brings us closer to knowing whether we've misunderstood the universe's heartbeat, or if the universe has been playing by hidden rules all along. When we picture planets, we imagine worlds forged from stardust rocky spheres rich in iron, silicon, and oxygen, or gas giants swirling with methane and ammonia. But the first planets, if they existed at all, would have been utterly alien, born in the aftermath of the universe's very first stars. These hypothetical worlds formed in a cosmos almost devoid of the heavy elements we take for granted. No iron cores, no silicate crusts, just carbon, helium, and traces of lithium, the sparse ingredients left by the Big Bang. In such a barren environment, planets wouldn't be made of rock or metal. They might instead be vast diamonds, graphite mountains, or even exotic helium crystals, glittering in the dim light of their massive, short-lived suns. The idea isn't as far-fetched as it sounds. Carbon, unlike heavier elements, was relatively abundant even in the early universe, produced in small amounts by the Big Bang itself. When population 3 stars, those first gargantuan stars, exploded as supernova, they would have flung carbon into their surroundings, seeding protoplanetary disks with the raw material for carbon-based worlds. Simulations suggest that in such disks, carbon could condense into graphite or even diamond under extreme pressures, forming planets with surfaces harder than any bedrock on Earth. Imagine a world where raindrops are liquid helium, where the ground beneath your feet is a single, unbroken crystal lattice stretching for miles. But could these planets have survived? The odds are slim, but not impossible. Orbiting stars hundreds of times more massive than our Sun, any fledgling worlds would have faced brutal conditions, intense radiation, violent stellar winds, and the constant threat of their host star's cataclysmic death in a supernova. Yet in the outer reaches of these systems, where temperatures were colder and material more stable, carbon-rich planets might have endured long enough to form. Some could even have been flung into interstellar space by gravitational interactions, becoming rogue planets adrift in the darkness, their diamond interiors preserving secrets from the dawn of time. The hunt for these primordial worlds is more than a thought experiment. If discovered, they'd prove that planet formation began far earlier than we ever imagined, reshaping our understanding of cosmic history. Astronomers search for them indirectly, analyzing the light from ancient quasars for signs of carbon absorption that might hint at intervening planets. Others simulate the chemistry of early protoplanetary disks, testing how carbon grains could clump together without the glue of heavier elements. every probe into this mystery forces us to rethink what a planet even is, how small a cosmic ingredient list can be and still assemble something familiar. What would life look like on such a world, almost certainly nothing like us? Without water or complex chemistry, these planets would be barren, their beauty locked in sterile geometry. And yet, their very existence would whisper a tantalizing possibility that the universe, even in its infancy, was already knitting together the pieces of places. Not just stars and gas, but worlds silent, glittering, and strange. The first planets may be lost to time, but if we ever find their remnants, we won't just be holding a piece of another world. We'll be touching the universe's first attempt at building a home. Our universe's cosmic dawn might seem inevitable, the only way things could have unfolded, but what if it's just one version of the story? Imagine a parallel cosmos where dark matter outweighs ordinary matter not 5 to 1, but 50. A universe where gravity is slightly weaker, or where the neutron's mass is a fraction heavier. In these alternate realities, the first light might never have pierced the darkness, or it could have blazed forth in ways beyond our comprehension. This is the multiverse hypothesis, the idea that our universe is one of countless others, each with its own unique physics, its own destiny written in the laws of nature. Take dark energy, for instance. In our universe, its value is perfectly balanced, strong enough to accelerate cosmic expansion, but weak enough to allow galaxies to form. Tweak that number slightly higher, and space would stretch so fast that matter could never clump together. No stars, no galaxies, just a cold, empty void. Turn it down, and gravity might have won, collapsing everything back into a singularity before life could stir. The cosmic dawn, then, wasn't just a phase, it was a razor's edge, a cosmic lottery ticket where the numbers lined up just right. Or consider the strength of the nuclear force. If it were even a few percent stronger, hydrogen would fuse into helium so violently in the first stars that they'd burn out in mere millennia. Too weak, and fusion might never ignite at all, leaving the universe forever dark. Some theorists argue that these fine-tuned constants hint at a deeper truth, that our universe is one of many, each with random physical parameters. Most might be stillborn, devoid of complexity. Ours, by sheer chance, had the golden combination. The wildest versions of the multiverse go further. In bubble universe models, new cosmoses constantly bud off from a frothing quantum foam, each with its own distinct physics. Some could harbor bizarre stellar factories where dark matter fuels star formation, creating black hole-filled galaxies. Others might have no stars at all, their skies illuminated by glowing strings of primordial energy. A handful could even host life, but built from entirely different building blocks, thriving in conditions we'd find lethal. While these ideas remain speculative, they're not pure fantasy. Certain interpretations of quantum mechanics and string theory naturally lead to multiverse predictions. Even cosmic inflation, the leading theory for our universe's exponential early growth, suggests that once inflation starts, it never truly stops, endlessly birthing new universes with varying properties. The cosmic microwave background might one day reveal anomalies, bruises from collisions with neighboring universes, or patterns in large-scale structure that hint at a broader cosmic landscape. For now, the multiverse is less a theory than a mirror, reflecting how strangely precise our universe's conditions appear to be. The cosmic dawn wasn't just a local event, it might be a signature of something far grander, a single note in a symphony of universes. And if that's true, then every star we see isn't just a point of light, it's a message. In this cosmos, against staggering odds, the darkness broke just right. The next decade of cosmic exploration won't just deepen our understanding of the universe's first light, it could shatter it. We stand on the brink of a revolution in observational power, with telescopes so advanced they'll peer deeper into the cosmic dawn than we've ever dared to dream. At the forefront is the Square Kilometre Array, or SKA, a sprawling network of radio antennas spanning 2 continents. When completed, it'll act like a time machine tuned to the dark ages, detecting the faintest whispers of hydrogen gas from an era when stars hadn't yet ignited. Picture this: maps of the universe as it transitioned from darkness to light, tracing the precise moment gravity's patience ran out and the first proto-galaxies flickered awake. But SKA isn't working alone. Space telescopes like Louvoir, a behemoth with a mirror 8 times wider than Hubble's, will hunt for the earliest galaxies in unprecedented detail. Where current instruments see only faint smudges, Louvoir could resolve individual star clusters within those ancient systems, revealing how they grew so massive so fast. There's even a chance it might spot the death throes of population 3 stars directly, capturing the ultraviolet afterglow of their supernova like cosmic flashbulbs in the void. And then there's the James Webb Space Telescope's successors, like the proposed Habitable Worlds Observatory, which could analyze the atmospheres of planets orbiting the universe's first stars' worlds bathed in alien light, their chemistry untouched by generations of stellar recycling. The real magic lies in what these tools might uncover unexpectedly. Theorists predict that the cosmic dawn could hide phenomena we haven't even imagined yet: exotic stellar objects powered by dark matter annihilation, primordial black holes distorting the fabric of spacetime, or even relics from pre-inflationary physics frozen in the cosmic web. Some models suggest the first stars didn't form alone, but in bizarre, hyper-dense clusters where collisions sparked energy bursts visible across the universe. Others speculate about cosmic strings, hypothetical defects in spacetime left over from the Big Bang, whose faint gravitational waves might still ripple through ancient gas clouds. What makes this era of discovery so electrifying isn't just the technology, it's the sheer scale of our ignorance. Less than 1% of the cosmic dawn's timeline has been observed directly. Every new instrument peels back another layer, but the universe has proven adept at surprising us. When Hubble first launched, no one predicted it would find galaxies mature enough to challenge our timelines. When Webb began its mission, scientists weren't prepared for the sheer luminosity of the earliest systems it spotted. The next generation of telescopes will likely append just as many assumptions, rewriting textbooks in real time. Perhaps the most profound question these tools could answer is whether the cosmic dawn played out uniformly across the universe, or if some regions woke early while others lingered in darkness, creating pockets of structure older than the rest. The implications would ripple through cosmology, forcing us to reconsider how finely tuned the initial conditions of the Big Bang really were. Whether confirming our theories or demolishing them, one thing is certain: the story of the universe's first light is far from finished. And as these new eyes turn skyward, we're not just observers of history, we're detectives on the verge of cracking the case wide open. Every atom in your body, every thought flickering through your mind, exists because the cosmic dawn unfolded with near impossible precision. The universe could have taken countless paths, some where stars burned too brightly and died too soon, others where galaxies never formed at all. Yet against inconceivable odds, conditions aligned perfectly to create a cosmos capable of giving rise to life. This isn't just luck, it's the anthropic principle in action, the idea that we observe the universe precisely because its laws allowed us to exist, and nowhere is this balance more delicate than in the universe's first chapters. Take reionization, that pivotal moment when ultraviolet radiation tore through the cosmic fog. Had it happened too quickly, galaxies might have been stunted, their gas stripped away before stars could fully form. Too slowly, and the universe could have remained opaque, trapping light in a suffocating haze. The timing had to be just right, allowing galaxies enough time to mature while still clearing the stage for starlight to travel freely. Even the first stars' masses were critical, too small, and they wouldn't have forged the heavy elements essential for planets and life. Too large, and their cataclysmic deaths might have sterilized entire regions of space with lethal radiation. The deeper we look, the more astonishing the fine-tuning becomes. The cosmic microwave background's faint ripples, those seeds of future galaxies, could have been stronger, leading to a universe clumped into black hole-dominated monstrosities, or weaker, leaving matter too diffuse to ever ignite stars. Dark matter's pull, dark energies push. Even the strength of nuclear forces each had to fall within razor-thin margins to allow for a cosmos where life could one day ponder its own origins. This precision doesn't merely shape our past, it guides our search for extraterrestrial life. If the cosmic dawn's conditions were this exacting, how many other universes, or even other regions of our own, might have missed the mark? Telescopes scouring ancient galaxies for biosignatures are essentially testing this cosmic lottery. Did other pockets of the universe hit the same improbable jackpot? The answer could redefine our place in the cosmos, revealing whether we're a statistical inevitability or a solitary stroke of cosmic fortune. Yet the anthropic principle isn't a conclusion, it's a starting point. Some scientists argue it hints at a multiverse, with countless universes bubbling into existence, each with random physical constants. In most, life never arises. We simply inhabit the one where the dice rolled in our favor. Others see it as evidence of deeper, undiscovered physics, a self-tuning mechanism woven into the fabric of reality. Either way, the cosmic dawn's legacy is clear. It's the foundation of our existence, the first domino in a chain stretching across 13.8 billion years. When we study this era, we're not just exploring ancient history, we're uncovering why there's anyone here to study it at all, and that transforms the night sky from a stranger's story into something deeply, intimately ours. One of the most persistent myths about the cosmic dawn is that it happened in a flash, a single, dramatic moment when the universe flicked on like a light switch. The truth is far more nuanced. This transformation unfolded over hundreds of millions of years, a slow-motion revolution where darkness gradually gave way to light. Think of it like a sunrise on Earth. It doesn't happen all at once. There's first light, then twilight, then full daylight. The cosmic dawn followed a similar rhythm, with the first stars sputtering to life in isolated pockets before their collective radiance finally burned away the cosmic fog. This wasn't an event with a clear start and finish. It was a messy, uneven process, with some regions of the universe emerging from darkness earlier than others, creating a patchwork of light and shadow across the young cosmos. Another common misconception is that we've directly seen the cosmic dawn. In reality, our telescopes capture only its aftermath, the echoes of those first stars and galaxies, their light stretched and dimmed by billions of years of cosmic expansion. Even the James Webb Space Telescope, our most powerful time machine, doesn't peer directly at the first stars. Instead, it detects their legacy, the chemical fingerprints they left behind, the way they altered their surroundings, and the shadows they cast on the hydrogen fog that once filled the universe. It's like trying to reconstruct a thunderstorm by studying the puddles it left behind. We're piecing together an era we can't yet observe directly, relying on clues scattered across space and time. Then there's the oversimplification of dark matter's role. Pop science often portrays it as some kind of cosmic glue, passively holding galaxies together. But during the cosmic dawn, dark matter was an active architect. Its gravitational pull didn't just gather gas, it sculpted the universe's large-scale structure, creating dense nodes where the first galaxies could ignite. Without dark matter's invisible scaffolding, ordinary matter would have been too diffuse, and stars might never have formed at all. Yet dark matter wasn't a uniform force. Tiny variations in its distribution meant some regions of the universe got a head start, forging stars and galaxies while others lingered in darkness. This unevenness is crucial to understanding why the cosmic dawn unfolded the way it did, and why some corners of the universe might have woken up earlier than others. Even the nature of the first galaxies gets distorted. They're often depicted as miniature versions of modern galaxies, orderly spirals, or neat ellipticals. In reality, they were chaotic, misshapen things, bloated with gas and prone to violent bursts of star formation. Their shapes were dictated by frequent collisions, their structures unstable. Some might have resembled bloated tadpoles, trailing streams of gas torn loose by gravitational interactions. Others could have been little more than tangled knots of stars, their forms unrecognizable compared to the majestic galaxies we see today. These weren't the polished cosmic cities of the modern universe. They were frontier towns, rough and raw, built in a hurry from whatever materials were at hand. Why does correcting these misconceptions matter? Because the cosmic dawn isn't just a chapter in a textbook, it's the origin story of everything. When we get the details wrong, we risk misunderstanding how the universe evolved, how common planets like ours might be, even how life itself became possible. Accurate science communication ensures we're working from the same cosmic blueprint, one grounded in evidence rather than speculation. Every myth we dispel sharpens our view of the past, helping us ask better questions about the universe's earliest moments. And in a field where new discoveries can rewrite history overnight, clarity isn't just helpful, it's essential. The cosmic dawn wasn't simple, and it wasn't instant. It was messy, uneven, and utterly fascinating. And the closer we look, the more we realize how much we still have to learn. From the silver screen to the pages of best-selling novels, the cosmic dawn has captivated storytellers as much as scientists, because what is cosmology, if not the ultimate origin story? Sci-fi classics like Contact, based on Carl Sagan's novel, weave the universe's infancy into their narratives, imagining alien transmissions buried in the static of the cosmic microwave background. The film's climactic journey through wormholes and celestial vistas taps into the same awe astronomers feel when studying those first moments of light, blurring the line between data and wonder. Even the three-body problem by Liu Cixin, with its chilling portrayal of an unstable three-star system, echoes the chaos of the early universe, where galaxies clashed and stars burned bright and fast. These stories don't just borrow from science, they expand it, asking what if with the same daring as the boldest cosmological theories. But pop culture's embrace of the cosmic dawn isn't just about spectacle, it's reshaping how the public perceives the universe's origins. Blockbusters like Interstellar turn black holes and time dilation into visceral experiences. They're IMAX-worthy visuals making abstract physics feel tangible. When a character peers into the fifth dimension or floats past a supermassive black hole's accretion disk, audiences aren't just watching a movie, they're glimpsing the consequences of cosmic evolution. Sometimes, though, dramatization oversimplifies. Films often compress billions of years into a montage or depict the first stars as Hollywood-friendly fireballs rather than the colossal, unstable behemoths they were. Yet even these exaggerations serve a purpose. They spark curiosity. A viewer might leave the theater and Google cosmic reionization for the first time, diving down a rabbit hole that starts with fiction and ends with real-world astrophysics. Then there's the darker side of pop culture's influence when creative liberty strays into outright myth-making. Some stories twist the cosmic dawn into a mystical event, framing it as a deliberate act of creation rather than the emergent result of physics. Video games like Destiny mythologize the Traveler, a celestial entity that terraforms planets, while Marvel's Eternals portrays cosmic energies as the work of godlike beings. These narratives aren't wrong, they're allegories, but they risk leaving audiences with a blurred line between science and symbolism. The challenge for scientists is to meet people where they are, bridging the gap between cinematic spectacle and peer-reviewed papers without dimming the wonder. What makes these stories so enduring, though, isn't just their scale, it's their intimacy. The cosmic dawn, at its heart, is about beginnings, a theme as personal as it is universal. When a sci-fi novel describes the first stars as lonely giants burning in the dark, it's not just painting a cosmic portrait, it's evoking the human experience of standing at the edge of understanding. That emotional resonance is why these tales endure long after the credits roll or the book closes. They remind us that science and storytelling spring from the same impulse, to make sense of the dark and to imagine what flickered to life there first. And perhaps that's the real magic of pop culture's cosmic obsession. Whether through a physicist's equations or a filmmaker's lens, the same questions haunt us all. Where did we come from? What came before? The answers may differ, but the longing to ask that's universal. Every retelling of the cosmic dawn, no matter how fictionalized, keeps that longing alive, ensuring the universe's first light never fades from our collective imagination. As we reach the end of our voyage through the 20 Chronicles of the Cosmic Dawn, it's worth pausing to reflect on just how far we've come, not just across these chronicles, but as a species peering into the abyss of time. These aren't just distant events frozen in the past, they're the foundation of everything we know. Every atom in your hands, every glimmer of starlight overhead, every galaxy spinning in the void, all of it traces back to those first, fragile moments when darkness gave way to light. What's astonishing isn't just the scale of these discoveries, but how recently they've come into focus. A century ago, we didn't even know other galaxies existed. Today, we're mapping the echoes of the first stars and decoding the universe's baby pictures, and this is only the beginning. Telescopes like the upcoming Nancy Grace Roman Space Telescope and the Square Kilometer Array will push our vision further, probing deeper into the dark ages, hunting for the whispers of those first molecules, or perhaps uncovering phenomena we haven't even dreamed of yet. The Cosmic Dawn isn't a closed book. It's a prologue, and we're turning the pages in real time. But beyond the science, there's something profoundly human about this quest. For millennia, we've looked up and wondered where it all began. Now, we're not just wondering, we're answering. Every flicker of data, every spectral line analyzed, every simulation run, brings us closer to understanding our place in this grand tapestry. And that's the real gift of these chronicles. They're not just about the universe's origins, they're about ours. So as we close this chapter, remember, you're part of the story too. The same forces that shaped galaxies forged the iron in your blood and the calcium in your bones. You're made of stardust, yes, but more than that. You're the universe waking up and wondering about itself. And that's worth celebrating, Drop a comment below which chronicle reshaped how you see the cosmos. Was it the violent births of the first stars, the invisible hand of dark matter, or the cosmic web's delicate architecture? Let's keep the conversation going. Don't forget to subscribe for more journeys to the edge of understanding. The cosmic dawn may be ancient history, but the adventure of discovery is just getting started. After all, the night sky isn't just a sight to behold, it's an invitation, and the universe has so much more to